Hey engineers, so what I'm going to do in this video is I'm going to do some truss analysis from the beginning to the end. I'm going to run through everything from start to finish, including calculating the reactions. All right, so let's go ahead and just make a start straight away, and I'll try and write down the steps as we go. Okay, so step one is to balance moments to find reactions. All right, so let's go ahead and do that. Let's make it nice and quick. Hopefully I don't make mistakes. I am quite sleepy again, but we'll see how we go. Here we go. So the sum of the moments about point A equals 0. And A is there. All right. So we got clockwise. I'm taking some shortcuts because this is a pain in the bum. Clockwise equals counterclockwise. Now clockwise, we have the 15 kilonewton here. 15 kilonewtons, and it's at a distance of, well, if this is 1.2, that's 1.2, that's 2.4 along the bottom, that's 1.2 there. So between this and this, that has to make up 1.2, so that means that this is 0.6. All right, so that is the perpendicular distance. Now, for just this one here, I'm going to run through and show you how that works. Now, if you imagine this 15 kilonewton force here, it's acting in this yellow line here. Check it out. That's the line of its action. So the perpendicular distance is going to be, well, what's a line that's perpendicular to that? Well, it's going to be that line there. So we take that along until it's in line with point A, or you could visualize it this way. It could be that distance there as well. So there's two ways to look at this. Either this distance here is 0.6 because of what we just talked about, or we're halfway along this member here, which is 1.2. So the perpendicular distance is also 0.6. There's a right angle there, right angle there. Okay, so that's a little bit of an explanation for those of you who are confused. We're always looking for the perpendicular distance to the force. So the force is acting in this line. The perpendicular distance is here. So it's 15 times 0.6. We also have that force there, which is 12. And it's got a distance of 1.2. Add half of this one, which is 0.6. So it's times 1.8. My screen thing's just going on. Hang on. All right, and they're the only forces we have going in a clockwise direction. Counterclockwise, we've got RBY times a perpendicular distance of 2.4. So there's RBY. So RBY has to be, now I'm not going to go through the maths here. I'm going to pause the video and do the calculation. RBY has to be 12.75. All right, 12.75 kilonewtons. Now you guys should know how to find that. So here we have 12.75. All right, now let's get rid of all that. Now, if I sum the forces in the X and Y direction here, I'm going to actually write it down. I'm going to do that to find RAY. Sum of the forces in the Y direction equals 0. So we're going to have RAY, add the 12.75, which is RBY. This is going up, equals our two down forces, which is 15 add 12. So all of this equals 27 on that side. If we take 12.5 from 12.75 from 27, we get, excuse me, I'm too lazy to do it in my head, 14.25. So RAY equals 14.7525. All right, 14.25. So that we've done this 1,000 times before. The only difference here is it's a little bit different finding the perpendicular distance because it's not directly sitting here. Our force isn't directly sitting right here. So the perpendicular distance is not as obvious, but it's really the same as if it was sitting there. It's the distance from here to the line of that force, so you can imagine it sitting right down there anyway. So we've got our two reactions. There's step one. Step two, we're going to label the truss joints. So that's where all of these trusses are meeting. So there's A, there's B, here is C, here is D. Now these might be labeled already in the question, so I'm not going to put it up as an actual step. Step two would be to cut this thing through the members that you want to find. So if I want to find BD, BC, and AC, I have to cut through all three of those. Okay, so if you have to just find the one BC, we have to make sure that we cut through it with a straight line. Don't go through more than 3 trusses, and I think you'll find it probably hard to do that unless you make a weird cut like that. Just go through 3 trusses, because if we have more than 3 unknowns, you won't be able to solve this. So step 2 is to cut the truss in half and create a new free body diagram for that. Okay, there's step 2 up there. Now, my cut is going to look something like this. I'm going to try and find BC, BD, and AC. Okay? So my cut's going to look just like this. Here we go. Let's do it in green. I'm going to make a cut right through those members. Okay? So we're going to take this half of the truss and we're going to recreate that free body diagram, but we're going to have to include the internal tensions of these trusses in our free body diagram. Okay, pause the video and do that for you. Okay, I've literally just erased the rest of the truss and we're going to draw in our tension forces now. So we have a force here coming out. We have a force here coming out, and we're drawing them coming out because this is pulling this tension apart. So it's in tension, which we're going to consider as positive, and that's general practice. All right. Now it doesn't really necessarily mean you're going to get things wrong if you draw things the other way, but we're just doing general practice stuff here. Okay. So there are my forces. This one here is FBD because it's between the joints B and D. This one here is FBC. This one here is FAC. So we can find them all. Now we talked about a couple of different methods to do that. This time I'm going to start by just summing the forces in the y direction to find FBC. Now the reason why I can do that is because FBC is the only unknown with a vertical component. FAC and FBD are purely in the horizontal direction. They do not have a vertical component. So what I know is that FBC, the vertical component of that, must balance out RAY and 15 kilonewtons, all right? So let's go ahead and do that really quickly. We got the sum of the forces in the y direction must equal 0. So for this free body diagram, the sum of the forces in the y direction must equal 0. So we got sum of the forces up equals the sum of the forces down. That's a D. All right. So in the upwards direction, we just have RAY. That's 14.25. That's the only thing we got. This one here. Downwards, we have the 15, and we also have the vertical component of FBC. Now we're going to have to do a little bit of trigonometry here. If we were to look at this triangle that FBC it's working in that direction there. So that's these are the components we're going to have to look at, the vertical component and the horizontal component. FBC is acting in that direction. So let's pull that out here. We're going to have to find out what that angle there is. Now I know that this distance here in this triangle is going to be 0.6. This distance here is 1. The height of this truss was 1 meter, remember? So that distance there, the height of the truss is 1. So here we go. So that's 0.6. That's 1. So let's quickly find the angle there. So we'll call that theta. So this is going to be a tan problem. So tan, because we have opposite and adjacent, tan theta equals 1 opposite over adjacent over 0.6. So theta is going to be the inverse tan of all that. I'm just going to do the calculation. All right, so we inverse tan that fraction, we get 65.6 degrees. Okay, now we can use that to say, we use the same triangle here, but that angle is there. Now this is FBC in this direction. So if I want the vertical component of that, this is going to be FBC sine theta. FBC sine theta. So in the downwards direction, we also have FBC times sine 65.6. All right, so FBC, when we solve all of that, is going to be equal to minus 0.875. Now the fact that this is minus, what does that tell me? Now a lot of you guys will get this right. That tells me that because we've drawn these forces in the positive sense as tension, if it's a minus, it's going in the other direction, so it's compression, okay? So we can say, therefore, FBC is 0.875 kilonewtons of compression. I would write compression the whole thing if I had a pen, but I don't. I've got paint. Ugh. All right, let's move on. Now, we've already found one of our forces here just by summing the forces in the y direction. Now, I'm gonna stop the video here, and in the second part, I'm going to sum the moments about this free body diagram to find the other 2 points, okay? I'll see you in the next part. Bye bye.